A round of applause for Linus.
Woo! There are 4 main vulnerabilities. So we have a code signature bypass, we have an arbitrary kernel read-write, we have a point authentication code bypass, and also a PPL bypass. And in the end, there will also be a short demo. Let me start with the first vulnerability, named FastPath, which is a CoreTrust certificate validation vulnerability. And this vulnerability is used to gain initial code execution on the device. Now, code signing, what is that on iOS? So on iOS, all executables that are run must be code signed. And this is enforced in the kernel by the Apple Mobile File Integrity kernel extension. There are 2 main types of code signatures that you need to know about. The first one is the ad hoc code signature, which just basically means that you have the code signature in the application, you have the correct format of the code signature, but there's no actual signer. It's just all the information contained in there that is required. And this is used for all the pre-installed applications. And essentially just the hash of that code signature blob in the file is known to the kernel. And if the kernel sees that hash, then it will automatically allow execution without doing any further checks. And the other type of signature are the CMS signatures. And this basically just means that in addition to containing the code signature blob, we also have a signature in there using a certificate. And importantly, a code signature can also contain entitlements, and entitlements is just a list of permissions that the application has. Now, how does code signature validation work? So if we assume that we are using a CMS signature, because, ad hoc signatures, we can just ignore them right now because, they are hard-coded, the list of signatures that are trusted, so let's ignore them. And, how does the CMS signature validation work? So if Apple Mobile File Integrity notices that an application does not have an ad hoc signature but a CMS signature, then it will delegate the validation of the signature to CoreTrust. And what CoreTrust does is it ensures that the CMS blob itself is valid and that the hash inside the CMS blob actually matches the hash of the code signature. Afterwards, after making sure that everything is correct, it will return some flags to Apple Mobile File Integrity that indicates the exact certificate type. Like, for example, it can indicate that it was signed, the application was signed using a developer certificate, or that it was signed using an App Store certificate. And importantly, CoreTrust will return success as long as the CMS blob looks valid. It does not verify the signer. This in itself is not a vulnerability, simply because, like for example on macOS, if you run an application, it might be signed using an MDM certificate that is not known to the kernel, but the application should be trusted nevertheless, simply because you manually trusted that certificate, but the kernel can't check that, so CoreTrust has to return success even if the signer is not trusted. What happens afterwards is, in Apple Mobile File Integrity, if the CT validation fails, it will reject the code signature and the application will not be allowed to execute. And otherwise, if the validation succeeded, then the CoreTrust flags will be checked. Now, if the CoreTrust flags indicate that the binary was signed using an App Store certificate, all further checks will be bypassed and the code signature will be accepted immediately. Otherwise, the Apple Mobile File Integrity daemon, which is a user space program, will then have a chance to validate the code signature and make sure that the signer is trusted. Now, I have this small flowchart that shows how it works. So again, we first check the hash of the code directory in the binary. If it's in the trust cache, we will accept it. Otherwise, we will perform a CT validation. And validation succeeded. If not, we will reject it. Otherwise, we get the CoreTrust flags. And if it's App Store signed, we accept the code signature. And otherwise, we request MFID to do the validation. Now, what is the vulnerability here? The vulnerability is that we directly take the CoreTrust flags from the certificate. And what that means is if there's a certain object ID present in the certificate, then the flags will be set accordingly. Now, if we include the App Store OID in the certificate, then CoreTrust will return that the application was signed using an App Store certificate. However, no further checks on the signer are performed. So, this is really a problem. Because if we go back to our flowchart, we now see that the CTA evaluation does not validate the signer. And if the evaluation succeeds, then we get the flags, which are taken directly from the certificate. And if we just claim to be an App Store certificate, then the code signature will be immediately accepted without any further checks, which is how we get the initial code execution. Now, how did Apple fix this? It's actually pretty easy. They now only return the flags if the certificate was issued by Apple. Otherwise, no flags are returned. The CoreTrust evaluation will still succeed, but the flags will remain 0. And this vulnerability is actually a regression because iOS 13 and below are not affected. They already do this check. Now, the next problem is, imagine that we have an app assigned using the fastpath vulnerability. The problem is, how do we get it onto the device? And the problem is we have install-D, which is responsible for app installation. And it does check the code signature of every app before installing it. And the problem is it is not affected by this vulnerability because it does a proper code signature check. So we need another vulnerability. Or do we? We can also just exploit this vulnerability again, which you might note from Fugu15. And the patch for this vulnerability is actually incomplete. So the thing is, it works out of the box on iOS 15. And the patch they did is just to make sure that, or let me first explain how the vulnerability works. So the vulnerability works by creating a FAT file, which contains 2 executables. The first one is an executable with a normal code signature, which the device will accept. And the other one is our executable. And we just create it in a way that install-D will validate the first application, but the kernel will run the second application. And the only check Apple added is to make sure that in the FAT file, the code signature of all the executables contained in it have the same team ID. And as long as we make sure that the team ID is the same, we just easily bypass that check. And using both vulnerabilities, we then have code execution on the device. Now, the next step for every jailbreak is to get arbitrary kernel read-write. And for that, I'm using the OOB PCI vulnerability, which is a vulnerability in PCI driver kit. And what is driver kit? Let's just look at what Apple says. So driver kit provides a fully modernized replacement for IO kit to create device drivers. And additionally, what Apple also says is, system extensions and drivers built with driver kit run in user space where they can't compromise the security or stability of macOS. We'll find out if that's true. But just as a small recap, what is driver kit? It's a framework for running drivers in user space. And it allows low-level access to devices. So you actually have more permissions than your normal user space application so that you can actually directly talk to devices. And these various methods are exposed to user space, and they were never intended to be used by untrusted code. But at least driver kit drivers must have an entitlement, so it's not that bad. Well, except that we have a code signature bypass and just grant this entitlements to us. So, Now, PCI driver kit is, driver kit for PCI devices, and it allows low-level access to them. Like, for example, you can just directly read and write PCI device memory. Now, all these methods for reading and writing the memory just take a memory index to select which of the memory banks you want to write into. They take an offset and a data parameter. And importantly, they take an offset. If we look at one of the functions that it provides, then we will see that it's actually not too complicated. So it exposes this function, which takes the memory index, offset, and data parameter. And then it will just get an I/O memory map object depending on which memory index you specified. And if that I/O memory map object is not null, then it will call MLIO write, which just directly writes to the first pointer passed in. And we just get the virtual address of the mapping we just got, add the offset to it, Then we write the data, and we also pass the size of the data. And yeah, the thing is, the memory index, this one is checked by a function called memory access, because we have to go through this memory access function. We cannot directly call this one. But the offset itself is not checked. It's not checked in memory access, and so it's fully attacker controlled, and it's 64 bits. And as you can see here, there are no checks to the offset, and we just directly take the virtual address of that mapping and add the 64-bit offset to it. There are no checks to make sure that the offset is actually within our mapping. Now, how can we exploit this vulnerability? The thing is, for Fugu15, I didn't want to use any kind of memory leak. So there are basically two strategies you could use. The first strategy would be to spray kernel memory. And then we could use the out-of-bounds access to leak and or modify kernel pointers. The only problem with this strategy is that the PCI device memory is part of the kernel data map. And the kernel data map, unfortunately, does not contain any kernel pointers, only user space data and some device mappings. So I'm using a different strategy here. The thing is, if you just repeatedly perform the out-of-bounds access and just write down the addresses you get in the panic reports, you will notice that the PCI memory address is actually deterministic. It's like plus minus 128 megabytes. And additionally, what we also know is that in the XNU kernel, all RAM is mapped as part of the contiguous fizz map. Now, the fizz map is located at a random offset after the kernel, and this offset can be up to 1 gigabyte. And the kernel load address itself is randomized also up to 1 gigabyte, which means that we have 2 gigabytes of randomization for the fizz map, but the problem is that modern iPhones have at least 4 gigabytes of RAM. So if we look at the memory layout, and for example, if we have no randomization, we just have the kernel directly here at, for example, this address. Please do not just copy that address. It's probably not correct. Just an example. And we then have the fizz map directly afterwards. If we assume maximum randomization, so the kernel is randomized by 1 gigabyte and the fizz map is randomized by 1 gigabyte as well, then the memory layout looks like this. And if we compare both, like this, then we will see that right here, this part, there's an overlap. So regardless of what the randomization value is, those addresses are also always safe to access, simply because there will always be RAM there. And so what we can do is we can just guess the offset to the fizz map from our PCI device memory, and then we can just scan the memory backwards to find the boot arc structure, which is always right at the start of the RAM. And once we found the boot arcs, we already know a lot about a kernel, so we can already just find out some addresses. But what we can then do is we can scan the initial page tables, which will be located directly after the boot arcs. And using these page tables, we can find out exactly where we are within the fizz map. So we can actually determine the offset between the start of the fizz map and where we are currently reading. And once we have that, we can calculate the distance between our PCI memory and the start of the fizz map. Additionally, what we also know is the fizz map is always located at an L2 boundary, which means that the fizz map starting address will have low 25 bits, will always be 0. And using a small calculation that you can see here, we can then just find out the lower 25 bits of our PCI memory simply by taking the offset between the PCI memory and our fizz map and performing this calculation. And afterwards, we can just scan the entire RAM to find our I/O memory map object. We can verify that we found the correct one by checking the lower 25 bits, and we can also check the size of the I/O memory map object. And once we found that, we know exactly where our PCI memory is located. And we can also check the vtable of that I/O memory map object and use it to find out exactly where the kernel is located and what the kernel slide is. Which means that we now have an arbitrary read-write in the kernel. And although we can already do quite a lot with it, on later iOS versions like 15.2, some mitigations were introduced that actually make jailbreaking quite hard. So Fugu15 exploits yet another vulnerability. This time, it's the bad recovery vulnerability, which is a point authentication code bypass via threat fault handlers. And as a small recap, point authentication codes, what is that? It's just a cryptographic signature for pointers, and it prevents the modification of critical pointers and data within the kernel, like, for example, return addresses that are stored on the stack. And it's also used to provide control flow integrity to prevent an attacker from redirecting the control flow and hijacking the PC register. Now, what are threat fault handlers? Threat fault handlers are a mechanism to handle expected faults during data accesses. It allows you to store a pointer in the thread struct, which is signed using point authentication codes. And if a data abort happens in the kernel and this fault handler is set, then the kernel will jump directly to it. What is this used for? This is an example. This is copy in. It's just a function to copy some data from a user space program to the kernel. And assume that a program does a syscall and passes in an address. And the kernel now needs to copy the data from that address and will use, for example, this copy in function for it. And it will first set the recovery handler to a function called copy.io error. And then it will try to load the X8 register from the pointer passed in X0. Now, if we assume that the user space program passed an invalid pointer or there's no memory there, then a data abort may occur. Normally, this would cause a panic, but because we expect this data abort to happen, the kernel will instead jump to copy.io error, which will just make sure that this function returns an error code. And now, we actually do have a function that has a vulnerability. It's kind of large, so it doesn't even matter what this function does. So I would just remove all the uninteresting stuff. And what this function does is it also sets a recovery handler. And the recovery handler is essentially just this code. And if you look at that code, you might think, where's the vulnerability in here? And the problem is this return down here. This is a normal return. This is not an authenticated return. And usually this wouldn't be a problem because this function does not ever change the link register. But we will soon see that you cannot assume that the link register is actually, has the value that it should have. Now, what is the strategy to exploit this? We can just call this function somehow, like machport modres will internally call this function. And what we can do is we can just steal the signed fault handler that will be set in our thread. Because we have arbitrary kernel read-write, we can easily just copy the signed thread handler. And what we can later do is we can just restore the fault handler and then perform a syscall. And if we now make sure that a data abort happens shortly after we do the syscall, then most of the registers will be user-controlled. Because if you do a syscall, every register will be user-controlled except for the stack pointer. Now, the strategy here is the kernel only accesses the user space register state before our registers are trashed. And the reason is the kernel obviously has to save those registers somewhere. And what we can do is we can just change the register state pointer in order to force a data abort. The only problem is that the kernel must be able to save the stack pointer, because if it can save the stack pointer, it will continue to use the kernel stack pointer and will then trigger a data abort. And if the stack pointer is set to the kernel stack pointer, to the EL1 stack pointer, then this will always cause a panic. So we need to make sure that it's able to save the stack pointer and then switch to the user space stack, which is also used in kernel mode as the kernel stack, but with a different value, obviously. So the solution is we just make sure that our user space register state is mapped up to the SP register and unmapped afterwards. So the kernel is able to save the stack pointer, and if it wants to save other registers later, then it just trigger a data abort. And Now, an additional problem is there's a stack check, actually. And when we trigger the data abort, the stack pointer will point to the top of the kernel stack. But the problem is that this check will kill us if that's the case. I'm not entirely sure why. They decided to check if the stack pointer matches the top of the kernel stack, but they do it, and this will actually kill us. So what we have to do is we just relocate the CPU's interrupt stack to somewhere else, make sure that our stack pointer overlaps with the interrupt stack, and then we will fail the first check, but we will pass the second one, which checks the interrupt stack pointer. And so what we do is as I said, we replace the kernel stack pointer and the CPU's interrupt stack pointer. Importantly, this will not actually change the CPU's interrupt stack because that's impossible, but it will change the stack pointer in that data structure, and the kernel will be able to verify it. After ensuring that the kernel stack pointer and the CPU's interrupt stack overlap, we will then pass all the checks. We will trigger the data abort, and we will be at the recovery handler right at this code. And the thing is, all registers except for x0, nx1, and the stack pointer are just completely user space controlled at this point. The other two registers, so x0 and x1, are not controlled simply because the kernel will trash them. But the others are. And we just have to make sure that this first macro, which expands to this, and just make sure that x16 points to some valid memory location so that the store succeeds. Then we'll trash the x0 register by writing 0 to it, and then we will return. And this return is an unauthenticated return, which means it will just use the value in the linked register and jump directly to it. It's just as I have explained. And so now we did an unauthenticated return. And which means we can jump wherever we want, and we control almost all registers. And using jump-oriented programming or return-oriented programming, we can then turn this into an arbitrary kernel call. And the thing is, one mitigation is still left. And I just cannot submit something without breaking all the mitigations present in iOS. So there's yet another vulnerability. This is the last one, I promise. And it's called TLB fail, which is a PPL bypass. What is PPL? PPL is the page protection layer. And it protects signed user space code and also some kernel data, especially on iOS 15.2 and later, from being modified even by the kernel. So it's essentially the last line of defense, and it's higher privilege than the kernel itself. And what PPL also manages are the page tables, because as PPL just prevents the kernel from writing to protected pages, it has to make sure that the kernel just can't modify the page table itself, because otherwise it could just map the protected memory. And it does provide some functions to the kernel in order to map an unmapped memory. But whenever you pass a page that you want to map, then it will obviously perform some checks to make sure that you're not trying to map PPL protected memory. Now, another feature we have is the so-called nested page tables. They are used for the DYID shared cache because the DYID shared cache is a large file. It's mapped into every process. And actually creating page tables for every process would consume a lot of memory. So what Apple decided to do instead is they nest those page tables. And what that means is if we have an example like this, so we have two applications, A and B, and both applications have the level 1 table, they have a level 2 table there, but they both map the DYID shared cache. And the DYID shared cache itself also has its own level 1 table and level 2 table. And then it has a level 3 table, which actually points to the pages in the DYID shared cache. And instead of applications A and B having their own level 3 table, they just share the same level 3 table, which then points to the page, which saves really a lot of memory. But the thing is, if you are having to do something to do with page tables, there's also a so-called translation look-aside buffer. A translation look-aside buffer is essentially just a cache for virtual to physical address translation. So if you access an address, the CPU will actually have to find out the corresponding physical address, and it will cache this translation. And whenever you change something in the page tables, you actually have to do a TLB flush, simply to make sure that the CPU does not use the cached entries anymore. And the thing is, these TLB entries may also have an address space ID. And the reason for that is if you have multiple applications that map data at the same address, then if you only change the page tables of one application, you also just want to flush the cache for that application and not for all the other applications. Now, the flushing is actually a bit complicated, but what this code essentially does is it checks if the page table you're operating on is a nested page table. If it is a nested page table, then what we have to do is we have to flush all entries regardless of the application address space ID present in that entry, simply because those entries are shared between multiple applications. And if we do changes to the DYID shared cache, then we have to flush the cache for all applications. Otherwise, if it's not a nested PMAP or not a nested page table, then we can just take the address space ID and perform a flush based on the address space ID. Now, the question now is, what would happen if we delete a nested entry through our applications page table instead of going through the DYLD shared cache page table? What would happen is, like, if we start like this, so we have two applications again, A and B, and we have the DYID shared cache here again. As you can see, the level 3 table is again mapped in DYID shared cache in both applications. And if we assume that both applications accessed this page X, then the translation look-aside buffer will contain two entries, one for the address space ID 1 and for address space ID 2, which corresponds to application A and application B. And we have both of these cached entries. And let's assume that we now delete the mapping to page X, not through the DYID shared cache, but through application B. What will happen is the code responsible for flushing the TLB will notice that we specified an application page table and will just flush the entry for application B, although it should have also flushed the entry for application A, which means that application A can, through the translation look-aside buffer, still access page X, but this page X now has a ref count of 0 and can be freely reused. And what we can do now is we can just tell PPL that this page X is now owned by PPL, and because the PPL just can't take arbitrary memory, so the kernel actually has to grant memory to the PPL. And after doing that, we can then still access this page X through the stale TLB entry. And so we just mark this page as being PPL owned, and we can still access it through the translation look-aside buffer. And we can force the PPL to actually reuse page X as a level 3 page table. Now our application A has this additional level 3 page table, but it can also directly write to the page table simply because it's still in the TLB. And what we just do is we create another entry in table 3, which maps our page X. And afterwards we just ignore. It doesn't matter if in the translation look-aside buffer if that entry is flushed at some point, because we now just created an entry that points to our level 3 table, and we can just directly write to our level 3 table now, and PPL is completely bypassed since we can just map arbitrary PPL protected memory. And so this is essentially all of the vulnerabilities in Fugu15. And the thing is, I know you want to see a demo now. And This will be partially a live demo, partially not, simply because I can't show the first part. It just takes way too long because, yeah, the Wi-Fi in here is not great. So, yeah, what you will also see here is how you get the Fugu15 app onto the device. So if I start this, what you can see here is I open Safari, and I go to my website, which has this nice tab here to install Fugu15 button. And just tap on it, and you will see jailbreakme.pinauten.de would like to install totally legit developer app. And yeah, I mean, what everyone would do now is just tap on install. And if we do that and go back to the home screen, then yeah, it will just start downloading. And this unfortunately takes quite a while because of the slow Wi-Fi. So if we fast forward a bit, then it's installed. And what you can see here is you don't see the Fugu15 app, but instead you see the Apple developer app. And the reason for that is I need a validly signed app in order to get Fugu15 onto the device, but I can use the install-d vulnerability to inject Fugu15 into that signed app. And if we open that, you will see Fugu install, which just installs the Fugu15 app onto the device and automatically opens it. Then you will be asked to, if you want to remove the developer app because it's not needed anymore. So just tap on remove. And yeah, you can just tap on Jailbreak, which takes a few seconds, and you get a success message, which means that iDownload, which is like a small application that I always include, actually yeah, is now running on the device. And if I now switch back to QuickTime, where is it? Or I just go on. Doesn't matter. So what we now have here is we have a log, which just shows everything that we have done. And yeah, back to the actual device, please. Oh, there we are. So this is my actual device. So I can actually show you, like, I'm currently on that device. And we can go back to the home screen. And we now have this shell here. I hope you can read that. So I have the shell here. Yeah, I could just type in help to see some of the available commands. But there's, for example, a kinfo command to just show where the kernel is mapped, the kernel base address. There's also an R64 command to read kernel memory. And additionally, we can also run bootstrap, which will install the processor's bootstrap onto the device. And if I now run UI cache -R to respring and go back to the device. This is my cat, by the way. Now we have Sileo installed, and we can actually open it. And you can tap on allow, and yeah, we have a package manager installed on the device, which is basically what every jailbreaker wants. And yeah. All right, so yeah, you can't install anything right now simply because rootless, and yeah, rootless is not really supported at this point. Yeah, but I mean, it works. And you can also run just arbitrary commands like in here, like, who am I or ID, so it definitely works. And yeah, just let me quickly go back to my presentation, and that's it. Any questions? Yeah, so it took me like a couple of months for the initial vulnerabilities like the fastpath vulnerability and the AOB PCI vulnerability For the other two vulnerabilities, yeah, to be honest, it took me like 2 weeks to find and exploit them because point authentication code and PPL bypasses are not that hard to find, to be honest. But yeah. Any other questions? I know that in iOS 16 there was added some new memory randomization stuff, and the PCI memory base address is just randomized more. But yeah, you could probably work around that by simply leaking a pointer. And, yeah.